Okay, thank you everyone for coming to our journal club today. We have an external speaker who's telling us about some of his recent papers. So it's my pleasure to introduce Tetsuya Hashimoto, who will be talking to us about the origins of fast radio bursts and their future applications. So thank you, Tetsuya. Go ahead.
Okay, thank you very much for giving me this opportunity to talk about our recent study. Good morning and good afternoon, everyone. I'm Tetsuya Hashimoto from National Tsinghua University in Taiwan. Today, I'm going to talk about origins of fast radio bursts and their future applications. Today's my talk is basically based on these recent our papers, which have published in monthly notice. Okay, just in case that you may not know the location of Taiwan. Taiwan is located here, so I'm connecting from here. It's 4 a.m. now. Thank you very much for changing time. Okay, so let me get started. This is outline of my talk today. Let me start with a brief introduction, and I will present our results, which include luminosity functions and number density evolution of fast radio bursts from our analysis. And then I will also talk about the future prospects of square kilometer array in future. And also let me talk about applications of fast radio bursts, especially focusing on the cosmic reionization history to be revealed by future FRBs and general relativity to be tested by FRBs. Then I will conclude my talk in the end. Okay, so probably I don't need to talk about details of the detailed introduction of fast radio bursts. Let me just quickly summarize the current situation of FRB. So as you know, there are so many theories of FRB origins. Then more than 50 theories have been proposed as possible candidate objects, progenitor of fast radio bursts. And then here I selected the possible candidates of FRB progenitors, which includes white dwarf, neutron star, stellar mass black hole, magnetar, young pulsar, supermassive black hole, supernova remnants. I don't go to the details of individual candidates, but the point here is that there are so many varieties. We really want to figure out which is the origin of fast radio bursts. So this is the current most important task in FRB research. Then recently there was a big news that one galactic repeating FRB was confirmed to be associated with a galactic magnetar due to your great works, CHIME FRB collaboration. So thanks to these great works, we know that at least one repeating FRB is associated with magnetar. However, we only know about one confirmed case, but we don't know at all about the remaining more than 99% of currently detected fast radio bursts. So this is actually a problem. Then, in previous research, try to localize fast radio bursts in the sky in order to reveal their origins. Actually, this is quite reliable method to reveal their origins. And then one confirmed case is very good, excellent example. However, I would say that observationally, this is not really easy. Therefore, increasing this localized sample is actually not really easy. Therefore, in order to overcome this problem, we changed our point of view. And then in this work, we uniquely focused on the history of the number density of fast radio bursts. So this is our point in our paper. Okay, so before going to the details, let me briefly discuss the difference between repeating and non-repeating FRBs. So as you know, okay, this is a schematic diagram of repeating FRB and non-repeating FRB. And then, due to the limitation of observational time, it may be possible that we are looking at only part of repeating FRB, like this situation. We are only looking at this one, maybe. And then we may misclassify this object as non-repeating FRB. So this may be the case because of the time limitation of observations. Therefore, in this sense, we even don't know whether or not the origin of repeating FRB is same as the origin of non-repeating FRBs. So even though this is a very quite basic question, but we still don't know if these two populations are really same or not. So in this point of view, we try to investigate the difference between non-repeating FRB and repeating FRBs in a statistical way. So this figure is from our paper. This y-axis is burst duration, which is corrected for instrumental broadening and rate of shoot broadening. Therefore, I say this is rest frame intrinsic duration in y-axis. As a function of luminosity of individual first order bursts. Sorry, when I say luminosity in my talk, actually that means energy. Sorry, just for simplicity, let me say luminosity, but actually this is in units of erg per hertz. So actually this is energy, more is, okay, just for simplicity, let me say luminosity. But anyway, so this duration and luminosity parameter space, I plot the repeating FRBs by red dots, and then non-repeating FRBs are blue dots. And these data are from FRB CAT project. Thank you very much. Thank you for Emily. And then, as you can see, we found that the locations of these two different populations are different in this parameter space. This figure may indicate that non-repeating FRBs are actually different from repeating FRBs. And we also investigate the so-called luminosity function in our papers. This is roughly speaking, the number density of FRBs as a function of luminosity, but luminosity is actually energy. Then there are several points in my luminosity function calculations. So let me explain. The first of all, we use the so-called Vmax method, which allow us to measure the density as it is. This is kind of traditional standard way to calculate the density, number density. So we do not use any model fitting when we calculate the density. And then based on the previous figure, we separate non-repeating and repeating FRBs in this analysis. And also we separate the different telescopes because there may be huge systematic differences between different telescopes. So we try to use homogeneous sample. And then we unify the definition of detection threshold, which includes the duration dependency. So let me a little bit talk about this in next slide. So, in different papers, sometimes they have a different definition of detection threshold of FRB. So we try to unify this detection threshold in this work. In two top panels here, I show the observed duration in y-axis as a function of observed fluence. This one is for Parkes radio bursts, basically non-repeating FRBs. This is CHIME FRBs. Red one is repeating FRBs. Okay, and then as you know, the detection threshold depends on not only on observed fluence, but also depends on observed duration. Therefore, if we plot the detection threshold, which is a kind of tilt line in this parameter space, then we try to we rotated these top two panels so that this duration dependency can be aligned along y-axis, which are shown in bottom two panels. And then here we plot the histogram of data points here. And then we define the detection threshold as the peak position of data distribution. So this is our definition of detection threshold. This is this one, sorry, the vertical line. But actually, this detection threshold is very similar to the nominal detection threshold reported in other literature. So anyway, we tried to unify the detection threshold for different telescopes for fair comparison. And then this is the result of our calculation of luminosity functions of first radio bursts. Y-axis is the number density of first radio bursts as a function of luminosity in units of erg per hertz. And then luminosity function of repeating FRB are marked by red circle here. And the luminosity functions of non-repeating FRBs are marked by blue circle here. Then In spite of different telescopes, we obtained more or less similar luminosity functions for different telescopes for non-repeating FRBs. And then there are 2 points here. First of all, the slope of luminosity function of repeating FRB is different from slope of non-repeating FRBs. And also at fixed luminosity, say 10 to the 30 erg per hertz, for example here, the number density of repeating FRB is significantly smaller, probably roughly speaking, 2 orders of magnitude smaller than the non-repeating number density of non-repeating FRBs. So in this sense, the luminosity function of repeating FRB is different from luminosity function of non-repeating FRBs in our analysis. So if I summarize these points, it seems that the repeating FRB is indeed different from non-repeating FRBs in terms of luminosities, durations, and luminosity functions. Then based on these things, my personal preference is that the origin of repeating FRB may be different from origin of non-repeating FRBs. This is our result. And then in next slides, let me explain. This luminosity function is actually useful to further constrain the origins of first radio bursts. So let me explain this point. Okay, then again, here I show the possible candidates of FRB progenitors. Then we can divide into 2 different types of progenitors here, roughly speaking. One is old objects with long lifetimes. For example, this has the more than giga-year timescale. They can survive almost forever. And another thing is young object with short lifetimes, which is typically mega-year timescale or even shorter. So they can survive only a young stage. So then point is that number density of this old object in the universe should be proportional to the cosmic stellar mass density because the stellar mass is dominated by old object in general. Therefore, then this cosmic stellar mass density is actually already measured from previous galaxy observations, which shows a nearly constant trend from present universe to the past universe. Past universe means, in my talk, past universe means rate of around 2. This is already measured from galaxy observations. Therefore, if FRB originates from this old objects, the number density of FRBs should also follow this nearly constant trend from present to past universe. Okay, and then in contrast, number density of young objects should be proportional to the activity of galaxies in the universe, because these magnetar, young pulsar, supermassive, active supermassive black hole, and supernova remnants, all of them are remnants from activity of galaxies. And then this activity of galaxies is also already measured from galaxy observations, which shows this is either star formation activity or black hole activity, supermassive black hole activity. Then anyway, this activity increased towards the past universe up to rate of 2. This is already measured from galaxy observations. And that means if FRB originates from this young objects, the number density of FRB should increase toward the past universe. Therefore, this number density evolution of first radio burst can strongly constrain the origins of first radio burst, either old object or young object. We can differentiate between these 2 populations using number density evolutions. This is our strategy. Then let me show our results. Okay, this is not our result. This is actually measurements from galaxy observations. So again, this is the number density in y-axis as a function of, say, this is look back time. Then, so for example, number density evolution of old objects, such as white dwarf here, is shown by yellow line. And the number density evolution of young objects, such as magnetar, is shown by blue line here. So either increase or almost constant. So let me show the number density evolution of non-repeating FRBs calculated from our paper, which are shown by red stars here. And then as you can see, we found that the number density of non-repeating FRB, this is actually from Park's sample. Number density of non-repeating FRBs are nearly constant over the past 10 giga years. This nearly constant trend is consistent with the constant trend of density evolution of old objects, for example, white dwarf here. And then this constant trend is not consistent with the increasing trend of magnetar, young objects. This result may indicate that the non-repeating FRB likely originates from old objects, such as white dwarf, or neutron star, or stellar mass black hole. And this one is preferable. And then, okay, again, I go back to the either increase or almost constant. And then I also show the number density evolution of repeating FRBs, which are shown by purple stars here. This is from CHIME data. And then we found that the number density of repeating FRB increased toward the past universe up to 10 giga year ago. And then this increasing trend is consistent with the increasing trend of young objects, for example, magnetar here. And then probably this is not really consistent with this constant trend of old objects. This may indicate that repeating FRB likely originates from young objects, for example, magnetar. So let me summarize this point. So observationally, there are two different populations of FRBs, non-repeating FRB and repeating FRBs. Then we found that number density of non-repeating FRB shows nearly constant trend over the past 10 giga year. This nearly constant trend is actually consistent with constant trend of cosmic stellar mass density evolution. Therefore, this may indicate that the non-repeating FRBs likely originate from old objects, including white dwarf, neutron star, and stellar mass black hole. In contrast to this, repeating FRB increased toward the past universe. Then this increasing trend is consistent with the activity of the universe, either star-forming activity or supermassive black hole activity. Anyway, this means that repeating FRBs likely originate from young objects, for example, magnetar, young pulsar, supermassive black hole, or supernova remnant. Then let me emphasize that this magnetar case is actually consistent with the one confirmed case for the galactic magnetar for repeating FRBs. Okay, so however, I note that the number of samples used in this analysis is quite limited. Therefore, CHIME's new data release can conclude this point. So I really want to collaborate with CHIME people to do this kind of statistical analysis using the revolutionary big data from CHIME. Okay, and okay, this is about the origins of first order bursts. And then in the remaining time, let me discuss applications of first order bursts. Let me discuss first the future prospects of first order bursts in the era of square kilometer array. Okay, so here I summarize the key sciences to be solved by future FRBs. So actually there are many topics here. So one is, of course, origin of first order bursts is really important in astronomy. And also the dark energy, especially the time variability of the dark energy, is supposed to be addressed by future first order bursts. And also cosmic reionization. First order burst is really sensitive to the cosmic reionization history. So therefore, FRB is really useful to address these things. Let me talk about this later. And also FRB is sensitive to the missing baryon problem, thanks to the dispersion measure. And then I will talk about this later. First order burst is also useful to test the general relativity. All of these things are key sciences in not only astronomy, but also in physics. However, currently available data set of first-order bursts is about 100, except for the CHIME sample. This 100 is actually too small to address these key sciences. Therefore, next question is how many FRBs will be detected in the future, particularly using a square kilometer array in my talk. So this paper was featured by Astrobytes. Please look at Astrobytes because this is very nice summary. And this square kilometer array, so you know, SKA will start science operation in 2020 in South Africa and Australia. SKA is big international collaboration between many different countries here. And then what's nice in SKA is their sensitivity and field of view. So if I compare PACS to SKA, actually the full operation of SKA will have 2 order of magnitude better field of view and also 2 order of magnitude better sensitivity compared to PACS radio telescope. Therefore, this figure clearly indicates that the SKA will bring a breakthrough in finding first radio bursts. Actually, this is the second breakthrough after the CHIME breakthrough. Therefore, many people expected SKA will find so many FRBs. Then, because I calculated the luminosity functions, by using our luminosity functions, here I predict how many FRBs will be detected using SKA. So y-axis is the number, expected number of FRBs. Actually, this is a cumulative number in log scale and as a function of redshift. Then non-repeating FRBs and repeating FRBs are shown by blue and red respectively. Then, okay, this is a cumulative number. Therefore, this number is always decreased towards the higher redshifts. And then you can see in my prediction, there is a range in y-axis here. This range is actually due to the different assumptions on redshift evolution of FRB luminosity functions, which is proportional to either cosmic star formation rate density or cosmic stellar mass density. Anyway, so we assumed the 2 extreme cases. Therefore, in reality, I think it would be between this range, I hope. Anyway, we found that the future SKA will detect 10⁵ to 10⁶ first radio bursts in total per year. And even at cosmic reionization epoch at redshift higher than 6, we expect 10⁵ 10⁴ FRBs. Therefore, these numbers are actually much larger than the currently available FRB sample. This number is, I hope that this number is large enough to address key sciences that I listed before. Then, using this expected number in future, I will discuss how accurately we can constrain the cosmic reionization history using future first radio bursts. So let me discuss the reionization history in next slides. The one sentence summary is that it's a new method. I propose a new method to reveal the cosmic reionization history using future first radio bursts. So this is the point of this talk, this part. Okay, so as you know, this is the artistic image of cosmic reionization history. You know, this reionization is latest phase transition of the universe from neutral to ionized states. This reionization is supposed to be related to the first formation of stars and galaxies. Therefore, this revealing the reionization history is a cutting edge, frontier of galactic astronomy. Then, observationally, there are 2 complementary ways to investigate cosmic reionization history. One is tracing neutral hydrogen, which uses quasar spectrum or 21 centimeter emission or absorption lines from atomic hydrogen. Then another way is directly tracing ionized materials in intergalactic space, which uses the cosmic microwave background CMB or fast radio burst FRBs. Because fast radio burst is categorized in this group, let me compare CMB and fast radio burst in my talk. Then let me first explain how CMB can constrain the cosmic ionization history in next slides. Okay, again, this is the cosmic ionization history. This is reduced 1100 and this is reduced 0. Then, as you know, cosmic microwave backgrounds propagates from reduced around 1100 all the way to the reduced 0 here. Then during this propagation of CMB will experience the Thomson scattering due to the free electrons in intergalactic space. Then by observing CMB, you can measure the optical depths of Thomson scattering, which is tau here. Then actually this tau is integration of electron density in intergalactic space over reduced 0 to 1100. Therefore, this tau, optical depth tau, is indicator of how much amount of ionized materials are there in the universe. Then, for example, if reionization happens at very distant universe here, for example here, we have more amount of ionized materials in between the ionization epoch and observer here. Therefore, we will expect a larger value of optical depth tau in this case. So in contrast, if the ionization happens at very nearby universe, for example here, you have less amount of ionized materials in intergalactic medium, in between observer and the ionization epoch. Therefore, you expect smaller value of optical depth tau here. Therefore, by measuring this optical depth tau, you can roughly constrain the averaged epoch of cosmic reionization history using CMB. So reionization epoch maybe here, maybe here, maybe here, or here, something like this. The problem here is that using optical depth tau, CMB can only constrain the averaged epoch of reionization. The CMB is actually not really sensitive to the detailed structure of cosmic reionization history as a function of redshift, which actually we really want to understand. This is the problem of CMB. And then in order to overcome this problem, we propose a new method to reveal the cosmic reionization as a function of redshift using future fast radio burst. This as a function of redshift, this point is the advantage of fast radio burst over CMB. So let me explain this point. So actually, this is a summary of actual situation, expected situation of fast radio burst in future. As I said, many FRBs are supposed to happen at distant universe at different redshifts. And then you can see so many horizontal white lines here. And then for each FRB, we can measure the dispersion measures. Then, you know, dispersion measure is actually very similar parameter to optical depth tau. Dispersion measure is also integration of electron density over redshift 0 to the redshift of each FRB. So the actual situation is like this. So unlike CMB, we see so many white lines here. That means we can measure the dispersion measure as a function of redshift in future. This point is really different from CMB. And then in our paper, we propose to differentiate this dispersion measure against redshift. If we differentiate this equation, we can directly get this electron density in intergalactic medium or ionization fraction of intergalactic medium. So this means that from FRB observations, we can measure this DDMDZ And then this ddmdz is actually directly proportional to the ionization fraction of intergalactic medium without any assumption on functional shape of the ionization history. So this is the advantage of our methods and FRBs. So for demonstration purpose, we assume three different reionization histories here, which are shown by red, different colors in this diagram. So y-axis is the ionization fraction of intergalactic medium as a function of redshift here. The point in this figure is that all of these three different reionization histories shows exactly same optical depth tau. Therefore, using optical depth tau, CMB cannot really distinguish between these different reionization histories. But I will say that FRB can differentiate between these. And based on the expected number in SKA error and these three different reionization histories, we constructed the mock FRB data in the SKA error, which are supposed to be observed in future. So this is shown in different panels here. Different panels correspond to different assumptions on reionization histories. And then this is dispersion measure in y-axis as a function of redshift. And then each data point in each panel corresponds to the one FRB mock data in future. Then mean of mock data are shown by black squares here. Then an important point in this diagram is the ddmdz. As I said, ddmdz is directly proportional to the ionization fraction in intergalactic medium that we really want to measure. Then in this parameter space, ddmdz is actually very simple. This is just slope of median mean data. Therefore, let's assume that we will observe this mock data in future. And then using this mock data, we try to reconstruct ionization fraction using our methods, ddmdz methods. Okay. Then here I show the reconstructed the ionization fraction from our mock data as a function of redshift here. Then reconstructed ionization fraction are shown by open circle and filled circle. And the original assumption on the ionization histories are shown by solid lines here. As you can see, this ionization fraction can be consistently reproduced by our methods. And then there are 2 points here. One is that as I said, CMB cannot distinguish between these different reionization histories because all of these show the exactly same optical depth tau value. However, FRB can distinguish using our methods. Especially, for example, this double reionization feature can be consistently reproduced by using our method and future FRBs. And another point is that FRBs allow us to measure the reionization history as it is, because when we deconstruct this ionization fraction, we do not assume any functional shape on the ionization histories. Therefore, we can reproduce any functional shape as it is. So these 2 points clearly indicates the capability and feasibility of future FRBs and our methods. Okay, so this is about cosmic reionization history. And then in the remaining time, let me briefly discuss the general relativity constraints by first relative burst. This is our newest paper, which was submitted to the monthly notice. Okay, so let me discuss. Here, I briefly summarize the history of general relativity. Starting from Newtonian mechanics, Isaac Newton proposed a great theory, Newtonian mechanics, which is great, more or less correct. But as you know, the Michelson-Morley experiments revealed that speed of light is always constant. This observation, this is experimental evidence cannot be actually explained by Newtonian mechanics. So this initiated the idea of general relativity proposed by Albert Einstein. And then currently, I think many physics people try to find new theory in physics after this general relativity. Therefore, it is good timing to go back to the accurately testing the speed of light, which may provide us a hint to find a new theory in physics. Then actually, this one, testing speed of light, FRB is really useful to test the speed of light. So let me explain. So in my talk, let me focus on so-called Einstein's weak equivalence principle, WEP. So WEP is a statement that speed of light is always same for different frequencies under the gravitational potential. Okay, this makes sense. So our Earth is located within our Milky Way, and the Milky Way is surrounded by many other galaxies here. And then these galaxy clusters create a huge gravitational potential. And then there is an astrophysical source, which is emitting photons at different frequencies, frequency nu1 and then frequency nu2 for photon 1 and photon 2. And then this general relativity, or WEP, assumes that the speed of light for photon 1 is exactly the same as the speed of light of photon 2 at different frequencies. Okay, I agree with this, so this makes sense. But I would say that it is always important to test the general relativity because this kind of test may provide us a hint to find a new theory. Therefore, let me try to check these things using first order burst. And then if there is a difference between the speed of light at different frequencies, we expect the time lag between the different frequencies for FRBs. Okay. The FRB is actually ideal laboratory because they travel the cosmological distances, and eventually we measure the millisecond very short time scale. So this is really sensitive to the slight difference of speed of light between different frequencies. And then actually, you know, when we detect first radio bursts, we do detect the time lag between different frequencies. This is observed frequency as a function of observed time. But you know, this time lag between different frequencies, so-called dispersion measure, is not due to the WEP violation. This can be explained by plasma effect dispersion measure, which is exactly proportional to the inverse square of observed frequency here. Then, you know, basically, when we detect first order burst, this curve is explained by this plasma effect only. Therefore, we do not really introduce this WEP violation actually. But in other words, if this WEP is violated, this signature must be within the observational uncertainty of dispersion measure. Otherwise, we should be able to detect deviation, clear deviation. But actually, in reality, we do not detect any clear deviation. Therefore, this WEP violation have to be within the observational uncertainty of dispersion measure. Then this fact actually place upper limits on the WEP violation using first order burst, actually observational uncertainty of dispersion measure. So people usually parameterize this WEP violation using delta gamma parameter, which is defined as gamma 1 minus gamma 2 for photon 1 and photon 2. And then this gamma 1 and gamma 2 must be exactly equal 1 if WEP is not violated. This is a GR case. Therefore, in GR case, delta gamma have to be exactly 0. That means if this delta gamma is non-zero value, that means WEP is violated. And then actually what we can do is we can put only upper limit on this delta gamma, which is shown in y-axis here in log scale, as a function of observed frequency here. Then previous constraints on delta gamma are shown by black markers, different black markers here. And then our methods using observational uncertainty of dispersion measure are shown by red dots here. One dot corresponds to one FRB. And then this is upper limit, so smaller is better in this figure. Then if you look at the most strongest constraint, for example, this one, is actually more than one order of magnitude better than previous works. So even though we do not detect any clear evidence of WEP violation, but I would say that it is important to accurately test the GR because this may provide us a hint to find a new theory. Indeed, we achieved the most accurate GR test than ever using first order burst. And I believe that this is a good addition in physics field. Okay.
You have 5 more minutes?
Ah, okay. I almost finished it. Okay, thank you very much. So let me conclude my talk today. My personal preference is that non-repeating FRBs are indeed different from repeating FRBs in terms of duration, luminosity, and luminosity functions. And then we found that non-repeating FRB likely originate from all the objects, such as white dwarf, neutron star, and black hole, stellar mass black hole. And then repeating FRBs likely originate from young objects in the universe, such as magnetar, young pulsar, supermass black hole, and supernova remnants. And then SK will detect so many FRBs, probably 10 to the 5 to 10 to the 6 FRBs per year. And then this number is really useful to constrain to reveal the cosmic reionization history using first order burst. And then we can also use the first order burst to test general relativity. Okay, I stop here. Thank you very much.
Thank you. That was a really interesting talk. All right. Okay, so I think we can open the floor to questions. If anyone has a question, feel free to either raise your hand or speak up. I see Vicky's already raised her hand, so go ahead, Vicky.
Hi, thank you so much for this wonderful talk. It's very interesting. I have a couple questions. One is when you refer to the possible young objects, you distinguish between a supernova remnant and a young neutron star or magnetar. And are you proposing that, or has it been proposed by anyone, that supernova remnants themselves? I mean, you need some compact object to get the millisecond time scale. So what do you mean when you say the supernova remnant as opposed to?
Actually, okay. So I think this is model dependent, but I think I'm saying that there is a model that predicts first order burst from actually there is a source, compact source at the center of supernova remnants. And then this creates a kind of interaction between the injected energy from this compact source and surrounding material in supernova remnants. So actually, I think there is a compact source here. So I really don't distinguish actually. This can be the young pulsar at the center. So.
Okay, thank you. And then the second question for the cosmic reionization, so you would need each of those fast radio bursts to have been localized with the redshift of the galaxy determined?
That's ideally case, yes, I think so. In this case, we have to measure independently redshift. So, but in my calculation, for example, 10% of redshift measurements for detected FRB would be enough, large enough to investigate this cosmic reionization history. Probably even photo Z, probably it would be fine because if we really want to achieve this level, for example, if you just need to achieve this level, I think photo Z will be enough because I really don't require very accurate measurement of redshift in x-axis. Then I think it is possible.
Okay, thank you.
Thank you very much.
Okay, Mohit.
Yeah, very interesting talk, Hashimoto. So I have a couple of questions. I think I'm not sure if I'm able to ask both of them. So the first one is related to the question that Vicky asked. Have you taken into account or have you corrected your fluences or observed fluences for the effect for the cosmological sort of redshift effect? What I want to say that have you corrected for K effect, or have you K corrected for when
Okay,
you are
so-
estimating this
Hello. Sorry.
Yeah,
Um,
go on.
Okay, maybe there was a network problem, but I guess you are asking about the K correction coming
Yes,
from the
that's right.
cosmological effects when I calculate luminosity.
True.
Is that your question? Oh, yeah, I included the K correction term. Yes.
And what is the factor? So what is the power law index you used?
Power law index, that's a good question. Because observation, it's difficult to decide the power law index. I just used the observed value from bright FRBs, which is measured for, I think, ASCAP bright sample. Masquerade measured the spectral index for bright FRB sample. Then I used maybe, in terms of alpha, I mean spectral index, that was, if I remember, minus 1.5, I think. I assumed this broad spectrum, broadband spectrum in my calculation. But this is quite uncertain, so maybe there is a room to improve this calculation.
Okay, thank you. And I'll ask the second. I think that's a quick one. So when you showed, I think for repeating FRBs, a plot where on x-axis it's look back time and y-axis is, I think, the rate or something.
Okay, let me show. Probably this one.
Yeah, this one. So for this FRB, the rightmost one, the look back time is around 9 giga-years. I think that is corresponding to redshift 1.5.
Yeah.
So I don't know which repeating FRB we expect to be at redshift 1.5.
Sorry, I didn't include a table in my slide, but maybe you can go to my paper, or other people also calculate the individual redshift using dispersion measure. So I think easiest way is please go to my paper, and then I think I gave a table.
Okay.
Of FRBs that was used for this calculation. So sorry, I don't know which is which.
No, okay, fine. Thank you.
Okay. I actually had a question about the weak equivalence principle slides that you showed. This is really interesting, and I hadn't thought about this before. What kinds of observations of FRBs would further constrain this? Like, how could you push even further down in that space?
Okay, I think this is actually measuring the photons with different frequencies. And then I think the better way is to go to small time scale, I think. So as you know, recently people try to go to very small time resolution, which is say microsecond level. And then this is actually millisecond level I'm using. If you go to microsecond level, probably I expect maybe 3 order magnitude better constraint from this. Then time resolution is probably a good way to further constrain. Yes.
Okay, thank you. Mohit, do you have another question? So your hand is still up.
Oh, no, I'm so sorry.
Oh, no, no problem. Just making sure that we got all your questions. Okay, are there any further questions before we conclude?
I actually have a question, Emily.
Go ahead.
Yeah, thank you, Tetsuya, for your talk.
Thank you very much.
I was wondering if the differences in the energy distribution or the luminosity distribution could also be described or explained rather by there being a difference in the average DM contribution of the host and local environment. That translate, which would translate into there being a systematic difference in the rescaling that you do using the DM measurement itself.
I'm sorry, I couldn't hear you very much. So could you repeat that point? Sorry.
Sorry about that.
Can you hear me? It's not clear.
It's clear? Okay, sorry about that. Yeah. I only had one earphone in. Yeah, so I was just wondering if you could explain possibly an alternate explanation for the energy distribution difference that you see between the repeater and non-repeating population. Mm-hmm. Could that actually be an artifact of there being a difference in the average DM contribution of the host local environment between the two?
That's a difficult question to me. I didn't consider about that before. In my calculation, I just simply assumed the same. I didn't differentiate the contribution from host galaxy between repeating and non-repeating FRBs in my analysis. And if you use systematically higher contribution for repeating FRBs, for example, probably that we expect, we get a systematically lower redshift for repeating FRBs. And then using observed fluence, we measure the intrinsic luminosity have to be lower redshift, means have to be smaller. Then what I get is actually in terms of luminosity, repeating FRB is actually fainter than non-repeating FRBs. Then if I assume different contribution for host galaxy components, then I think this difference goes further away, I think. If we assume higher contribution from host galaxy for repeating FRBs, that we expect, right? Then I think this population gonna become, how to say, difference becomes larger, I think.
Yeah, I suppose you could play the game in the opposite direction, where you assume the two distributions are the same, and then adjust the DM host contribution.
Yeah. In this case, I assumed the same DM contribution from host galaxy. Yes.
Okay, thank you.
All right, and then last question. I see Vicky has her hand up again. Go ahead, Vicky.
Yeah, thank you. So I unfortunately I arrived at your talk a little bit late, and I hadn't quite seen the slide. And I have a question. Repeaters are often observed with, large telescopes because they know where to observe them and target them. And Arecibo when it could, or FAST now more recently. Therefore, they're able to detect fainter repeat bursts. So have you corrected for the fact that a lot of the faint repeat bursts that you see here are because there's been greater exposure with large single dish telescopes that have small fields of view that would not be finding any non-repeaters?
Okay, thank you very much. That's in this figure, there may be that kind of observation bias. There may be, because we tend to target repeating FRBs using a more sensitive telescope. That makes sense. Yeah, there may be systematics here, observation bias here. So we have to correct. But in this diagram, I just plot the currently available sample. So we need to caution. We need a caution. But in terms of luminosity functions, this is using homogeneous sample. For example, for repeating FRB, we use only CHIME telescope. I mean, FRB is detected with CHIME, for example, this one. And then if I compare to the luminosity function for non-repeating FRBs using only CHIME, which are shown by gray here, because at this moment, this was maybe commissioning phase, then they give only the upper limit on the survey volume. So therefore, this luminosity function gives only lower limits in this case. But anyway, in terms of luminosity functions, I do see the difference between non-repeating and repeating FRBs using the same CHIME telescope. This is survey type telescope. So therefore, CHIME should be free from that kind of observation effect, I think. Therefore,
no, sorry.
Sorry. So therefore, in terms of luminosity function, it seems that these two are different.
Is it okay to ask a follow-up question?
Yeah, go ahead.
For the CHIME repeaters, are those all of the repeaters that CHIME has reported, or only the first burst from the repeater per source? And I ask because when we detect a repeater, when we detect an FRB, then in some cases we lower the threshold. Yeah, so ideally you would be using only the first detections of the repeater when doing this analysis.
I believe that this is CHIME discovered repeating FRBs, I believe. So, you know, there is a famous paper about the repeating FRBs from CHIME group. I'm just using that paper. They found about 20, in total 20, about 20 repeating FRBs. I'm using that sample. So, sorry, I don't know the details of their strategy to detect, but I guess this is originally discovered from CHIME telescope. But I should be careful about that point. Yes, thank you very much. Yes.
Okay. Thank you, Vicky. All right, so we are at the hour, so we will conclude here. I want to thank Tetsuya for a wonderful talk and for waking up so early to deliver it for our collaboration. So this is all very interesting, and thank you so much. I'll stop the recording.